Hello. This isn't our normal class time or anything, but I'm going to post a solution for a little more complicated problem. I think this could be useful for you. So um, there's been some questions about problems involving blocks and planes and pulleys, and there was a question. So this is sort of a pretty complicated one. So we'll set this one up, and you can kind of have this as being as a reference. So let me read the question for you. So the masses MA and MB slide on the smooth, frictionless inclines fixed as shown. A, determine a formula for the acceleration of the system in terms of MA, MB, theta A, theta B, and G. And if then they give us some numbers for those quantities and ask us what MB would keep the system at rest. And they also ask us to solve for the tension of the cord. And then they also ask us, what ratio of masses would allow the masses to move at a constant speed along their ramps in either direction. So this question is fairly complicated, so we didn't talk about it in class, but I figured it might be nice to have this as kind of a reference and to be able to look at a question, a worked out one that's just where the algebra is a little more sticky. So, okay. As we've done with other problems like this, the first thing that we're going to do is let's draw free body diagrams for each of the masses. So for MA, what do we have? Well, how we're going to approach this also like the inclined plane problem that we looked at, where we're going to tilt the coordinate system to make it easier to analyze. And actually, we're going to have two different ones. We're going to tilt on either side of this ramp. And we can do this because the pulley changes the direction, so it's okay if our coordinate systems are broken separate like this. Okay, so let's draw free body diagrams for each. For MA, what do we have? Well, we're going to have force of gravity pointing down. We're going to have normal force pointing perpendicular to the surface. We're going to have also this tension force that's along the surface. Okay, and then we're going to want to break this force of gravity into x and y components along our axis. So the y piece is going to be cosine theta A, and the x piece would be sine theta A. And actually, these are both MA. And also, it's important to note that these are both negative. And that you can see if you look at the coordinate system, this piece is in the negative y direction, and this piece is in the negative x direction. Okay, so let's see. So that would be, and we have theta here. So that's for MA. And you can already see why this problem is a little more complicated because we have two angles floating around. So for mass B, similar kind of situation. B trying to draw this as neatly as I can. Same kind of thing. We would have mBg, force of gravity down, the normal force pointing perpendicular. We would have then similarly, we're having our coordinate system oriented along the slope, so we would have this component along and component perpendicular. Oh, I should have noted here, this is theta A. And for this one, you can see this would be theta B. As you shrink that angle, it's going to get smaller. Okay. And we don't want to neglect here the tension force. It's pointing that way. So those are our components for the forces. And we're going to assume, just to help us keep our signs straight, that the acceleration is in this direction. So in other words, MB and MA, for that matter, will be moving in the positive x direction, accelerating in the positive x direction. We got to put in our components. So this would be MBG sine theta. And then this would be MBG cosine theta. Okay, so I think that's got all of our pieces. What else? And actually, let's be careful here. This one would be negative, because notice it's in the negative y direction relative to our coordinate system. Okay. All right. So we could sum the forces in y, although since there isn't any friction, all this would tell us would be what the normal forces are, respectively, for MA and MB. This would be an issue. This would be relevant if we were looking at friction, but we're not. So this is a frictionless situation. So we don't really, all the action is happening in the x directions. So let's look at the two masses, sum of the forces in x. So if we look at MA, you can see that we would have a positive tension. We would have a negative mg sine theta A. That negative, that component of gravity that's in the x direction. And this would be, these are the only two forces on that in the x direction, and these would sum to ma acceleration A, let's call it. Or we could call it AX or whatever. All right. And then if we look at MB, some of the forces in X for MB, what do we have? Well, we're going to have negative tension force. Notice the tension is to the left in this coordinate system. We would have positive MBG sine theta B. Just put in B's over here. And what is this going to equal? This would equal MB AB X. And now note that the acceleration AX and the acceleration BX, these are both positive. So when one goes to the right, the other one also goes to the right. And since these objects are connected together, the size of those will be the same. So in other words, AAX we're just going to call this A. So we can simplify this a little bit. So I've sort of made it deliberately a little more complicated and then show you explicitly how those two are the same. Okay. So now we have, what do we have? We have two equations, two unknowns. We don't know either tension or the acceleration. So let's solve for A. How do we do that? Actually, let me label our expressions here. So we have these two equations. What we can do is we can substitute in and solve for it. So let's take our top expression. Go from so from 1, we know that the force of tension is going to be mass A times acceleration plus mass A g sine theta A. And then let's substitute that into our expression from number 2, where we have, well, here, let me just write it out, and then you can see where we're going to put it in. So our expression 2, rewriting it, we would have the negative force of the tension plus mb g sine theta b is going to equal mb times A. And then we're going to substitute what the tension force is into there. So just being really explicit about the parts here. Okay. And so you can see now we have, no longer do we have the tension in our expression. So we can then solve this situation for A. So how do we do that? Let's put all the A pieces on one side. Let's see, so we would have MBA plus MAA is going to equal MB G sine theta B minus MA G sine theta A. And then we could, factor out this A here. And then divide by that factor. And so we would end up with A is going to be all this stuff divided by MB plus MA. G sine theta B minus MA sine theta A. Okay. So we have a big, ugly expression for the acceleration. And let me just redraw our picture here so we have it kind of on the same page. Okay, so we can do a couple things. Let's check the units. So what do we have? We have a factor of mass times acceleration over mass. So this will have units of meters per second squared, which is what we want. We can also look at what's going to happen in the limits. So for example, if MB is very large relative to MA, that'll make the MA piece negligible, and we would just get G sine theta and vice versa. So if MA, is much bigger than MB, sorry, I might have switched those. I can't remember exactly. But if MA was very large compared to MB, for example, then the MB term would be irrelevant, and A would go to negative G sine theta, i.e. it would go, this way. And negative G sine theta is just what we expect from the block on a ramp. And, similarly, if MB was really big relative to MA, then what would happen? Well, the MA term would go away, and we'd be left with MB, the MB term, and that would be G sine theta B. And that would be, this way, and that would agree with our intuition for just a block on a ramp if we made the other one negligible. So that sort of agrees with our intuition. Okay, so what else did they ask us to do? They ask us, let's see, part B, for MA being 5 kilograms, theta A being 32 degrees, and theta B being 23 degrees, what MB would keep the system at rest? So what we can do is we can look at where this acceleration would be 0. And in that case, if it was at rest, it would stay at rest. So what that means is we want to know where the numerator of this would be 0. So I'll just write copy the top of our acceleration expression here. Where would this be 0? Well, we can then solve that relationship for MB. So what do we get? We would have MB is going to equal MA G sine theta A divided by this stuff, G sine theta B. If we then put in our numerical values, oh yeah, I guess these G's would cancel. If you crunch the numbers, you find that this would be a mass of 6.8 kilograms. So that would be the mass that would, where if the system was just at rest, it would stay at rest based on these angles and a mass A of 5 kilograms. Okay, and then what else do they ask us? So part C, they want to know, they want to know also what's the tension in the cord. So to find the tension, we can refer back to our expressions 1 and 2. And now that we know MA, we can, and MB, we can plug that information in. So what's the tension in this situation? Well, if we look for our tension expression, we had that it was, the tension is MA times acceleration plus MA g sine theta A. So in this case, there's no acceleration because it's balanced. So we would just plug in MA g sine theta. MA was 5 times 9.8 times sine of 32 degrees. And we find that in this situation, this would be 26 newtons. So that would be the tension force when A equals 0, when the acceleration is 0, when it's balanced. Okay. And then the last bit of the question is asking us what ratio of masses would allow the masses to move at constant speed along their ramps in either direction. So this is actually kind of a trick question. Well, it's not a trick question, but it's another way of asking the same question. So they want to know what ratio of MA over MB allows constant speed. So if it's moving, remember this is sort of not an easy situation to visualize, but we're assuming that there isn't any friction. So if there wasn't any friction, if it's moving, it's going to continue to move. So if it's moving at constant speed, that would mean that the acceleration is also 0. So it's another way of asking us the same situation. And if they want to know MA over MB, we already calculated an MB and for a given MA. So that would just be our 5 over 6.8. About 0.74 would be the MA over MB that allows constant it allows motion with constant velocity. So hopefully I'm posting this question basically as kind of a reference because it's a little more involved and we didn't have time to talk about it in class, but maybe this will be a complement, a guide for a more complicated question as you're working through questions on your own. I like the idea of posting questions that are similar but not the same as what you're doing because one of the things that we want to learn, and it's tough, it's kind of the most difficult part of learning physics, I think, is you have to develop a sense of like, well, when do I do what? And if you're basically only doing questions that you've already seen before, it's tough to exercise that muscle. And so I'm going to present stuff that's similar, but not exactly the same to what you're asked to do. And then hopefully you can kind of take those pieces and build from them and be able to exercise your problem solving skills so that then as we go forward, as you encounter more problems where you have kind of less guidance, you'll be able to come up with ways to apply what you've learned. So yeah, thanks for your patience with this online adventure, and hopefully this problem is useful to you as well.